Hi guys, so we have this question on complex numbers which reads, state De-Moivre's theorem on complex numbers and use it to prove that a complex number z is equals to x plus iy is equals to r cos theta plus I sin theta has exactly n distinct nth roots. All right, so let's start by proving this part first. Then we're going to go ahead and solve the equations that follow. That is, we'll be finding the fourth root of 16, the cube root of 8, and every other equation that follows. So let's break it down. All right, so state De-Moivre's theorem on complex numbers and use it to prove that the complex number, this one given, has exactly n distinct nth roots. So to start with, De-Moivre's theorem states that if I've been given a complex number in polar form, that is cos theta plus I sin theta, and this is raised to the power n. This is equals to cos n theta plus I sin n theta, like this. Now, please note that this is also equivalent now to if I have the modulus of a complex number, cos theta plus I sin theta, then all this is raised to the power n. This means that z is equals to r raised to the power n, then open bracket cos n theta plus I sin n theta. Okay, so this is a De-Moivre's theorem. Now, to prove the complex number has exactly n distinct roots, we're going to say let w be an nth root of z. So this means that w raised to the power n is equal to z. So if that's the case, let's write w in polar form. So if we write it in polar form, this means that w is equals to, now let me avoid r, let me use p to represent the modulus, then cos phi plus I sin phi. This is just what I have here, same thing, but I'm just using different letters just to differentiate what we're doing. So if I use the De-Moivre's theorem for this, it means that now I'll have w raised to the power n is equals to p, open bracket, cos phi plus I sin phi raised to the power n. So if I push in that n by using the De-Moivre's theorem, then this will become p raised to the power n, open bracket, cos n phi plus I sin n phi, like this. So if that's the case, I can relate this to now to the expression that I had here. This expression, let me bring it here. We can say wn is equals to z. If that's the case, then p to the power n, open bracket, cos n phi theta plus I sin n phi is equals to, now z in polar form is simply r, open bracket, cos theta plus I sin theta. So clearly I can compare the modulus. So if we equate the modulus, we can see that r is equals to p to the power n, or p is equals to, so I'll raise both sides to the power 1 over n, so that would be r raised to the power 1 over n. Because what I've done here is, I've simply said right hand side, this is 1 over n, Same thing here, 1 over n. So this n cancels that n, then I have that expression that I have there. So we are saying that p, let's remove this, p is equals to r to the power 1 over n. Now let's equate the arguments as well. If I equate the arguments are just the angles in this case. The angles will be n phi is equals to theta. But remember, if this is in generalized form, then this will be 2 pi k. So this means that phi is equals to theta plus 2 pi k divided by n. So based on this information, this is how we can now present it. So this means that wk will be equals to, remember, w in polar form was p n open bracket cos n phi plus I sine n phi. So if I replace phi and p, then this will be k is equals to r to the power 1 over n, like this, multiplied by cos. So now I have this expression that I have here, which is replacing our initial angle, which was phi. So it will be cos open bracket theta plus 2 pi k over n plus I, again sine theta plus 2 pi k divided by n. Now in this case you can say where k is simply 0, 1, 2, 3, going all the way up to n minus 1. So now if we increase k beyond k minus 1, this is what will happen. That expression that we have there will be, the angle expression will be theta plus 2. So let me just put in the words so that it makes sense. You can say if we increase a k beyond n minus 1, that is the term that we have there, this means that the expression will simply be theta plus 2, where there's k, to be k plus n. Because remember, we increase it beyond n minus 1. Now this is multiplying pi and divided by n. This will be equals to theta plus 2k pi over n, and to this we're just adding a complete revolution, which is 2 pi. Now when we say it's equals to plus 2 pi, we're simply saying it's going to be repeated over and over again. So we can say, which gives us repeated values. So what I mean by this is, suppose I have the Argand diagram like this, then my complex number is, for example, right here. If I add 2 pi to this, it's more like I'm saying I rotate it 360. This will rotate in this direction and it will still come back at the same point. So it will be repeated at the same point because you are simply adding 360 to it. It's more like turning on the right, on the same point. So a non-zero complex number has exactly n distinct nth roots. That's what we're saying. So that's how we show it. Find all the fourth roots of 16. So to start with, this can be written as z is equals to 16 raised to the power 1 over 4. because this represents the fourth root. Remember, this is as good as saying the fourth root of 16, something like that. So now, if we have it like this, this is a completely real number because on the Argand diagram, this is the imaginary of z. In this direction, this is the real of z. Now we know that in this direction, the angle here is 0, the angle here is 90, the angle here is 360. No, sorry. The angle here is 180. The angle down here is 270, like that. So this means that our complex number is 16 and it's real, meaning that the angle theta is simply 0 degrees because it's completely real. There's no imaginary part attached to it. Alright, so now that we know our theta, it means that we can write it in polar form as z is equals to 16, open bracket, cos 0 plus I sine 0 degrees. Now remember, all this is raised to the power 1 over 4. For your own information, cos 0 is 1, sine 0 is 0. So if I multiply I and 0, get a 0 of course. So this gives us 16 multiplied by 1, which is just the 16 that we had originally. So meaning that those two expressions are just the same as 16 if you write it in polar form. Now, what if this was a complex number, for example, 16i? We know that if it's I on the Argand diagram, the theta for positive I will be 90 degrees. If it's negative I, like this, then our theta will be 270 because it's pointing downwards. If it's negative real, then theta will be negative 180. So it's just all about the direction that it's taking. Alright, so now we have this expression. I can write the generalized version of this, which will be written as z is equals to open bracket 16 raised to the power 1 over 4 times cos, so that's 0 that we have. We simply add a complete revolution to it, which is 360, but in this case allow me to use 2 pi. So 2 pi k plus I sine 2 pi, or rather 0 degrees plus 2 pi k, a complete revolution. And this is raised to the power 1 over 4. So z is equals to the fourth root of 16. So here I was supposed to remove the bracket because we pushed the 16 outside. So it's supposed to be something like this. Then open bracket inside here. This is just a 0. So I'll just remain with cos 2 pi k plus I sine 2 pi k raised to the power 1 over 4. Now, please note that this k is representing the values 0, 1, 2, 3. So 4 values of k because we want the fourth root of k. So, for this bracket that we have here, I can use De-Moivre's theorem, which states that if I have cos theta plus I sine theta raised to the power n, then this can be cos n times theta plus I sine n times theta. So if I apply De-Moivre's theorem, what I will obtain will be z is equals to fourth root of 16 is simply 2, then open bracket, so that 1 over 4 multiplies 2 pi k. So we're saying 1 over 4 multiplied by 2 pi k. According to De-Moivre's theorem, that's the n theta I'm talking about, this one here. So our n is 1 over 4. So this gives us pi k over 2. So this will be written as cos pi k over 2 plus I sine pi k over 2. Okay. So this is the only expression that I need to find the 4 values that we're looking for. So let me obtain this expression. Let's just put it here. So remember, we said where k is 0, 1, 2, 3. So let's start with k being 0. If k is 0, what is z? Z will be 2, open bracket, cos 0 plus I sine 0. So this will be equals to 2, cos 0 is 1, sine 0 is 0, so this just leaves us with 2. How about when k is 1? What is z? Z will be 2, open bracket, cos. Remember, if k is 1, then we only remain with pi over 2 plus I sine pi over 2. Like that. So cos pi over 2 is 0. Sine pi over 2 is 1. So this just leaves us with 2i. How about when k is 2? What is z? So we'll say 2, open bracket, cos. If k is 2, then that will be 2 over 2. The 2 over 2 cancels, leaving us with pi. So it will be cos pi plus I sine pi. So this will be equals to 2. Now cos pi is negative 1. Sine pi is 0. So that gives us negative 2. Lastly, what if when k is 3? So when k is 3, means that z is equals to 2, open bracket, cos, remember, k is 3, so it will be 3 pi over 2, plus I sine 3 pi over 2. So that's just 270 if you are using degrees, so it will be 2, cos 270 is 0, sine 270 is negative 1. So this is equals to negative 2i. So the 4 roots of 16 are 2, 2i, negative 2, and negative 2i. Alright, so let's find all the cube roots of 8. So to start with, what we're looking for is z is equals to the cube root of 8. So this means that z is equals to 8 raised to the power 1/3. So now in polar form, remember this is just a real number and it's positive. So this means that z is equals to 8 multiplied by cos 0 degrees plus I sine 0 degrees. And all this is raised to the power 1/3. So this bracket that I have here, cos 0 is just 1, sine 0 is 0. So if I multiply that with 8, I'll still get back to the 8 that I had. So that's how I write this particular complex number in polar form. So why am I choosing 0? Because on the Argand diagram, this is the real axis, and going in this direction is the imaginary axis. Now our number is just 8, so it's in the real axis and it's positive. So the angle in this direction is simply 0. Here it's 90, here it's 180, down here it's 270. So since it's real and it's positive, then the angle is just 0. So that's why. Okay, so our next step here, we can say z is equals to, so 8 raised to the power 1/3 multiplied by cos 0 plus I sine 0 raised to the power 1/3. So z is equals to the cube root of 8 multiplied by, so this here will be cos we can say cos 0 plus 360k. It's just a generalized version, plus I sine 0 plus 360k, like this. This is 0 to the power 1/3. So z is equals to the cube root of 8 is simply 2, open bracket, then that's just a 0, so it will just remain with cos 360k plus I sine 360k. Now at this stage I'm going to use De-Moivre's theorem, which states that if I have the polar form of a complex number, that is cos theta plus I sine theta raised to the power n, then this can be written as cos n theta plus I sine n theta, like this. So now, if we look at what we have here, our n is the power 1/3. So we can say z is equals to 2. So that 1/3 multiplies with the 360k. For your own information, k are the numbers 0, 1, and 2, because we want the 3 solutions to our question. So if that's the case, let's go back here. So 2, open bracket, cos. If I multiply 360k times 1/3, it will look something like this. 1/3, 360k. Plus I sine 1/3 times 360k. This is according to De-Moivre's theorem. This means that z is equals to 2, open bracket, cos. 3 can go into 360. Remember, we're dividing by 360 over 3, and that gives us 120. So cos 120 degrees plus I, there's a k here, sine 120k, like this. So this is the expression we're going to be using to find the 3 solutions that we want. So let's start with k being 0. If k is 0, what is z? Z will be equals to 2, open bracket, cos 0 plus I sine 0. Because k is 0, so it multiplies everything, in just case it's 0. So this means z is equals to 2, 1 plus 0. So z is equals to 2. Okay, how about when k is 1? What we get? When k is 1, z will be equals to 2, open bracket, cos 120 plus I sine 120. So z is equals to, so the cos of 120 is -1/2, and sine 120 is positive √3 over 2. So this means that z is equals to -1 plus I √3. How about when k is 2? What do we get? Z will be equals to 2, open bracket. So remember, this k here is a 2. So that will be 240. So if it's a 240, then we're saying cos 240 plus I sine 240, again, like this, So this means that z is equals to 2, open bracket. Now, cos 240 is negative half. Sine 240 is negative root 3 over 2. So this means that the complex number z will be 2 times negative half is negative 1. 2 times negative root 3 over 2 will simply be negative I, the root of 3. So there we have it. In this case, we can clearly see that z has the solutions 2 and negative 1 plus I root 3. And lastly, negative 1 minus I root 3. So it was just a matter of replacing k in this expression that we have here with starting with 0, then k with 1, then k with 2, just like that. That is what gives you the expression that is required. So let's find all the fifth roots of negative 32i. So we can first say, we can write our complex number like this. This is equals to negative 32i. Now, since we're looking for the fifth root of this, we can say this is 5 fifth root, like this, of which z is equals to negative 32i raised to the power 1 over 5. Now, we need to write this in polar form. Now, we have to be careful here because, number one, this is an imaginary complex number only, and it is negative. So, if we look at the Argand diagram, which is this one right here, we know that going up in this direction, this is the positive imaginary of z. Going down is negative imaginary z. Going in this direction is the positive real of z. And in this direction, we know that this is negative. So since this is an imaginary number and it's negative, meaning that it's going downwards, and we know that going downwards, the angle here will simply be 270 degrees, which is equivalent to 3 pi over 2. So for this one, allow me to use degrees and not radians so that you just know how to do both of them. So writing this in polar form will be z is equals to that 32 will be written like this. 32, open bracket, cos, remember the angle is 270 degrees, plus I sine 270 degrees, raised to the power 1 over 5. Now this 1 over 5 is for everything. Now these two are the same, because if you say cos 270 is 0, and sine 270 is negative 1. So negative 1, let me just show you what I'm talking about. This part here gives us a 0. This part here gives us a negative 1. So this means that I just have negative I. And if I multiply with that 32, which is outside, I'll still get back a negative 32i. That was talking about. So we've written this in polar form. Now after that, we need to apply De-Moivre's theorem. But before we do that, we can say z is equals to this 32 that you see here will have 32 raised to the power 1/5 multiplied by cos 270 plus I sine 270. Okay, using radians, this will be 3 pi over 2, like I said. So now, this also has the power 1/5, like that. So that 1/5 will multiply our angle in. But before that, the fifth root of 32 is 2. Then the generalized version of this polar form will be cos 270 plus 2 pi k plus I sine 270 plus 2 pi 2 pi k, like that. Now remember, this is raised to the power 1 over 5. If I apply De-Moivre's theorem, we know that De-Moivre's theorem says that if I have, for example, cos theta plus I sine theta, this is raised to the power n, that n can multiply our angle like this, plus I sine n theta. So now our angle is 1 over 5. So let that 1 over 5 multiply the angle that we have now. So z is equals to, the fifth root of 32 is 2. 1 over 5, so we'll say cos. Now I'm not supposed to use 2 pi because I'm using degrees. So instead of 2 pi's, I'll use 360. Let me just remove that. I forgot about this. Because these things, in most cases, you have to use radians. It's much easier in radians. So this is actually 360 degrees. So here, 360k. So that 1 over 5 is multiplying our angle according to De-Moivre's theorem. So that will be 270 plus 360k over 5. Because it's multiplying the whole thing. So if it's multiplying the whole thing, that 5 just goes in the denominator. Plus I sine, the same thing again, we'll say 270 plus 360k divided by 5. And just that you know, this k we're talking about are the values 0, 1, 2, 3, and 4. Because this will give us the 5 roots that we're looking for. Alright, so let's just remove everything. And let's see how we can obtain the 5 roots that we're talking about. So once you have the generalized version, which is just this, your job is just to replace k with those values. So what happens if I replace k with 0? What do I get? This means that z will be equals to 2 cos, so that's a 0 to cancel out, meaning that just remains 270. So 270 divided by 5. So 270 over 5. What is 270 divided by 5? So this is giving me a 54. Let me just remove all this. So this just gives me 54. 54 degrees plus I sine 54 degrees. Okay, so I can find the actual value of this. So this is when k is 0. Because remember, this is zk. So when k is 0, I get this. How about when k is 1? What do we get? So z1 will be equals to 2 cos. If k is 1, then we're saying 360 plus 270, which is 630, and we divide that by 5, giving us 126. So the angle there is 126 degrees plus I sine 126 degrees. Remember, you can find the actual values of this. You just don't want to find them because they'll give me decimals, but you can find the actual values of these. So K2, which is Z2, this will be equals to 2. So if I replace K with 2, then I'm saying 360 multiplied by 2 plus 270 divided by 5. I'm getting 198. So cos 198 plus I sine 198. Okay. How about when K is 3? What is Z3? So Z3 will be 2. Then 360 multiplied by 3 plus 270 divided by 5 is 270. So that will be cos 270 plus I sine 270. So for this one, I want to get decimals because this will simply be 2 0 plus I times negative 1. So our answer here will simply be negative 2I, of which you can find the same for all of them, but I'm just avoiding decimals, but you can go ahead and do it if you want to. So for the last one, when k is 4, this means that z4 is equals to 2, open bracket. So 360 multiplied by 4 plus 270 divided by 5 gives us 342. So cos 342 plus I sine 342, like that. Find the 60th root of unity and represent them on an Argand diagram. Okay, so the 60th root of unity are the complex numbers that satisfy the equation z raised to the power 6 is equals to 1. So we can write 1 in polar form. Remember, the polar form of a complex number can be written as r cos theta plus I sin theta. In this case, our r is 1, so we're just going to have it as cos. Since 1 is a positive real number, then we'll just say cos 0 plus I sine 0, like that. So this means that z power 6 is equals to 1 in polar form is cos 0 plus I sine 0, like this. So in this case, clearly theta is 0. Theta is 0 degrees. And the reason why we've chosen theta to be 0 degrees because when you look at the Argand diagram, this is the imaginary axis, this is the real axis. So simply, because we just have 1, which is just real, that's why we're getting the angle there to just be 0. So I can write this as z power 6 is equals to cos theta plus I sine theta, of which I know that my theta is 0 degrees. So the generalized version of this will be z power 6 is equals to cos theta plus a complete revolution, that's 2 pi k, plus I sine, again, theta plus 2 pi k, like that. But remember, our theta is 0, so this means that z power 6 is equals to cos 2 pi k plus I sine 2 pi k. 2 pi k, like this. Now, it's important to note that on the left-hand side, we have a power 6. So to get rid of that power 6, I'm going to multiply both sides by, or raise both sides with the power 1 over 6. So first of all, k is just the list of positive integers. And in this case, since we want 6 roots, then we'll say k is equals to 0, 1, 2, 3, 4, 5. This gives us k having 6 values. So to get rid of this power 6, I'll say z is equals to, open bracket, cos 2 pi k plus I sine 2 pi k. And all this is raised to the power 1 over 6. Because I multiplied both sides, I raised both sides with power 1 over 6 so that that cancels out. So now, if this is the case, then I can use De-Moivre's theorem. Now, applying De-Moivre's theorem here, De-Moivre's theorem says that the power that I have there can multiply with the angle that I have inside there. So it will look something like this. So according to the theorem states that if I have cos, let's say theta, plus I sine theta, then this is equals to, first of all, this is raised to the power n. Then this is equals to cos, that n multiplies theta. Also here, that n multiplies theta. So now, the n that we have in this case is 1 over 6. So we have to convert, or rather, that 1 over 6 must multiply with the angle. So it will look something like this. We'll say z is equals to, open bracket, cos 1 over 6 times, so I'll say 1 over 6 multiplied by 2 pi k. Then plus I sine, again 1 over 6 multiplies 2 pi k. We know that k is just that the value is 0 up to 5. So this means that my z, I can now say z subscript k because it is in terms of k. So z subscript k is equals to, the 2 can cancel, leaving us with something like this, cos pi k divided by 3. If I reduce it, plus I sine, same thing, pi k divided by 3. Alright, so now, how do we proceed from here? So to start with, what we have as zk, we have cos pi k divided by 3 plus I sine pi k divided by 3. But remember, we know what k is. K is 0, 1, 2, 3, 4, 5. So now I can go ahead and start replacing that. So when k is 0, what happens? So if I replace k with 0, it means that zk will be equals to cos 0 plus I sine 0. If I replace k with 0, this will just be 0, that will be 0. So now this is a z0. So z subscript 0. This whole thing just gives us 1, like that. And we know that 1 is completely real, meaning that if this is the complex number, then theta is simply 0 degrees. And that's the point that we have right here. So if this point here is 1 positive, this one is 1 negative. Remember, this is the imaginary axis. Then this here represents the real axis. So this is a positive 1 again. And down here we have a negative 1. So the complex number, z0, is simply 1 and it's at 0 degrees. So let me label it here as, this is here is our z0. So we'll do the same. When k is 1, we're finding z1. This means that I replace, remember, I'm replacing in the original expression that I have on top there. That will be cos, since k is 1, it will be cos pi over 3 plus I sine pi over 3, like this. So this means that z1 is equals to, now, cos pi over 3, this is just a cos 60. The cos of 60 is half, plus the sine of 60, or pi over 3, is root 3 over 2. Now for this one, it is at an angle 60 degrees. And it's a complex number that I have right here as z1. Now, some of you might not understand where the 60 degrees is coming from. In simple terms, this 60 degrees is simply the argument of what we have. Let me quickly show you. To find that 60 degrees, just find the argument. Remember, argument is found by theta is equals to the tan inverse of the imaginary part, which is root 3 over 2, divided by the real part, which is half. So theta is equals to the tan inverse of root 3 over 2 multiplied by 2 over 1. Of which this is simply equals to, the 2 can cancel, leaving us with the tan inverse of root 3. And the tan inverse of root 3 is 60 degrees. So that's how I obtained that 60 degrees. So for the next complex numbers, I'll just be finding the angles without showing you, because now you know where it's coming from. The angle is simply you finding the argument of that particular complex number. So if that's the case, let's also find the complex number when k is 2. So if I replace in the original, remember the original replacing is this one that I have here on top. I'm just replacing k in this one here. So if I replace k with 2, I'll get cos, I'll say z2 is equals to cos. So now it will be 2 pi over 3, like this, plus I sine 2 pi over 3. So the complex number in question is this one right here. This here is our z2. So the complex number, if this reduces, if we find the exact value of cos 2 pi over 3, if you use radians, you'll get negative half plus I root 3 over 2, like that. Okay, so for this one, it's at an angle theta. Theta is at 120 degrees. All right, so now we know what is happening. So let me just write everything as 1. Let's just remove this. So when k is 1, the complex number z1 is half plus I root 3 over 2, where theta is 60 degrees. When k is 2, z2 is the complex number, negative half plus I root 3 over 2, for theta being at 120. Remember, to find the 120, you just have to find the argument. So when k is 3, z3 is equals to negative 1. And negative 1 is at an angle 180 degrees. Right here. So this here is our z3. So next, when k is 4, this is z4. This is the complex number, negative half minus root 3 over 2. And the theta for this one is simply 240 degrees. And that's the complex number that we have here. So this here is our z4. So for the last one, when k is 5, it means that z5 is equals to the complex number half minus I root 3 over 2, with theta being at 300 degrees. So this here is our z5. So these are the 6 complex numbers that we obtain. So now we're going to connect these 6 complex numbers. So connecting these complex numbers simply forms a hexagon like this. So once that is done, we can now connect those points and you'll see that a perfect circle will be formed. And we obtain something like this. So this is when all the points are connected. First of all, if you just draw lines, we're going to form a hexagon, but a circle can be formed as well. So there we have it. All right, so let's determine the roots of z squared plus 4 is equals to 0. All right, to start with, z squared is equals to negative 4. Now, this negative 4, we can say negative 4 can be written as 4 multiplied by negative 1. Then this negative 1 in polar form can be written as cos pi plus I sine pi. Now, you might be asking me, say, why are we choosing pi? Remember, from the Argand diagram of complex numbers, this represents the imaginary of z, and this represents the real of z. But we know that the angle that is formed here is 0. The angle formed here is pi over 2 or 90. Angle formed here is pi. And since we only have -1, then we know that -1 is in this direction because this is the real axis having the negative sign. Okay. So from here now, we can say if -4 can be written like this, it means that z squared can be written as 4, open bracket, cos pi plus I sine pi. Then to get rid of that square that I have there, I can simply say I square root both sides. So I introduce a square root to both sides, and we know that the square root is just power half. So this side I have 4 cos pi plus I sine pi. Now this whole thing is raised to the power half, which is just a square root. So z is equals to 4 raised to the power half multiplied by cos pi plus I sine pi raised to the power half. Now, according to the De-Moivre's theorem, we know that if I have the expression cos theta plus I sine theta, if this is raised to the power n, then that n can multiply our theta like this, plus I sine n theta. So if that's the case, that half will multiply my angle pi. This means that z will now be expressed as 4 to the power half, just as good as the square root of 4. Then open bracket, so I have cos half times pi gives us pi over 2 plus I sine, again half times pi will simply be pi over 2, like that. So the generalized version will be z is equal to, now the square root of 4 is 2, open bracket, so this will become cos, now pi over 2 will be pi plus 2 pi k divided by 2, like this, plus I sine pi plus 2 pi k divided by 2. Alright, so from here, this k that we have, k represents positive integers, rather positive integers with 0 inclusive. So starting from 0, we can go all the way. So these are just whole numbers. But in this case, we only want 2 solutions because z was raised to the power 2. So this means that we can say when k is 0, what do we get? So let's replace k with 0. This will be z is equals to 2, open bracket, cos, so that will just leave us with pi over 2, plus I sine pi over 2. Pi over 2 is just 90 degrees. So z is equals to 2. Cos pi over 2 or cos 90 is 0. Sine pi over 2 or sine 90 degrees is 1. So that would be I. 1 times I, simply this. So this means that our value of z here will be 2i. So how about when k is 1? What do we get? So z will be equals to 2, open bracket, cos. If I replace k with 1, I will say pi plus 2 pi, which is 3 pi over 2, plus I sine 3 pi over 2. So this means that z will be equals to 2. Now 3 pi over 2 is just the same as 270 degrees. So cos 270 degrees is 0. Sine 270 degrees is a -1. So if I multiply everything that I have in the second solution, will simply be 2, negative 2i. So there you have it. These two right here are the two solutions for our complex number. So how can we solve this particular equation from the topic of complex numbers? First of all, it's important to note that this is a typical quadratic equation to start with, because it's in this format. But in this case, we have our z squared and our z representing x. So let's obtain the coefficients, then we can solve it using the quadratic formula. So the coefficient of z squared, which is our a, is simply 1. The coefficient of z, which is our b, is negative, open bracket, 3 minus I. And the constant c, in this case, is simply 2 minus 2i. So z is equals to negative b plus or minus the square root of b squared minus 4ac. All this is over 2a. So let's substitute. Z is equals to negative. Now remember, our b is also having a negative. So that would be negative, negative 3 minus I plus or minus the square root of negative 3 minus I. This whole part is supposed to be squared minus 4ac. Now our a is 1, while our c is 2 minus 2i. All this is over 2a. A is 1, so it's over 2. So all this is over 2. So z is equals to, so if you're pushing that negative, then it will become positive. So just have it as 3 minus I. Negative and that negative gives us a positive like that, plus or minus. So inside the bracket there, we'll say we have the square root of. So the negative squared will be positive. So only remain with 3 minus I squared minus, so here we'll have 8 plus 8i. All this is over 2. Now just a quick simplification over what we have as 3 minus I is multiplying with 3 minus I because it's expanding. So 3 times 3 there will give us 9. 3 times I will give us 3i. I times 3 will give us 3i. And negative I times negative I will give us minus 1. So 9 minus 1, that will be 8. Then minus 6i. So this is giving us 8 minus 6i. So z is equals to 3 minus I plus or minus the square root of. So this squared simplifies to 8 minus 6i minus 8 plus 8i. Remember, all this is over 2. So if that's the case, let's remove this. So this means that z is equals to 3 minus I plus or minus. So inside the square root there, we have 8 minus 8, which will be a 0. So this 8 and this 8 cancels out, we'll get a 0. So the only thing we'll remain with is negative 6i plus 8i, and with that will give us 2i. This is over 2. Now, negative, the root of 2i is a question on its own. So let's simplify that part first. We'll come back to our question. What is the square root of 2i? So the best way to break this down is by first writing it as 2i. So 2i in polar form will be 2 multiplied by cos. Now remember, we want the I. This is positive. So if it's positive and it's I, that's the y-axis in the Argand diagram. And since it's positive going upwards, that is 90 degrees. And 90 degrees is simply pi over 2 plus I sine pi over 2. Now, cos pi over 2 is 0. Sine pi over 2 is 1. So 1 times I is I. So I times 2 will get back the 2I. So to this expression that I have here, I can introduce a root to both sides, introduce a root there, introduce a root there. So the square root of 2I is equals to root 2 multiplied by open bracket cos pi over 2 plus I sine pi over 2. Remember, we had the square root for this part, so that's power half. Now, if I apply De-Moivre's theorem, this half should multiply the angle that we have, which is pi over 2. So, root 2I will be equals to root 2 multiplied by open bracket cos pi over 4. We've applied De-Moivre's theorem, I sine pi over 4. Like this. Now, cos pi over 4 is root 2 over 2. So first of all, you can say root 2I is equals to root 2. Cos pi over 4 is root 2 over 2. Sine pi over 4 is also root 2 over 2. So the square root of 2I is equals to root 2 times root 2 over 2 will simply be 2 divided by 2. Same thing here, to be 2 divided by 2, I. So this is equals to 1 plus I. This means that the square root of 2I is equals to 1 plus I. So if we go back to our question, we can now replace the square root of 2I. So this will be Z is equals to 3 minus I plus or minus 1 plus I. And all this is over 2. So Z will be equals to 3 minus I plus 1 plus I divided by 2. Or Z will be 3 minus I minus 1 minus I divided by 2. So Z is equals to 3 plus 4, sorry, 3 plus 1, that will give us the 4 I'm talking about. So we'll have 4 over 2, because the I and the I cancels out. One is positive, one is negative. So the other value will be Z is equals to 2 minus 2I. This is over 2. So our final answers for Z. The first value for Z will be 2. Or the other value for Z will simply be 1 minus I. So there you have it. That's how we solve this particular equation. Alright, so let's solve this equation from complex numbers. So we have Z cubed is equals to negative 8. Alright, so allow me to write this as Z cubed is equals to 8 multiplied by negative 1. Now, our focus first of all is on the negative 1. If we're writing this in polar form, negative 1 is in this direction. This is the negative 1 direction. This direction here is a positive 1. So first of all, we can clearly see that in this direction, this is the angle 180 degrees, or pi if you are using radians. So we're going to write it in polar form in this way. We're going to say that negative 1 can be written as, so I'll say since cos pi plus I sine pi is equals to negative 1. Now if you understand what is happening here, remember sine pi is 0 and cos pi is negative 1. So this whole thing can just replace that negative 1. So our equation now can be written as Z cubed is equals to 8. Where there's -1, I'll replace that with cos pi plus I sine pi, like that. Okay, so now our next step, to get rid of that cube that I have there, I'll simply introduce a cube root to both sides. So I'll simply say I need a cube root here and I need a cube root here. So the cube root cancels the cube, left hand side, leaving us with only z. Right hand side, we have the cube root of 8 multiplied by, now remember, cube root is the same as a power 1/3, so this is open bracket cos pi plus I sine pi raised to the power 1/3. So at this stage, if I use De-Moivre's theorem, this becomes, first of all, the cube root of 8 is simply 2. So I'll just write it as 2. So I'll say 2 open bracket. Then I'm using De-Moivre's theorem. So this will be cos 1/3 pi plus I sine 1/3 pi, like that. Okay, so just a quick reminder, De-Moivre's theorem states that if I have the number, let's write like this, if I have the number r, cos theta plus I sine theta, this is raised to the power n, and that n can become the power of r, like this, and then the theta multiplies n. So I'll have cos n theta plus I sine n theta. Now in this case, our n value is simply 1/3, and our theta was pi. So I'm saying 1/3 multiplied by pi, hence we have this expression. Now what we want is to find 3 values of z, simply because z is raised to the power 3. So to generalize it, we're going to write it like this. Z is equals to 2 open bracket. So I have the cos. Then inside the bracket there, I will say pi, that's the angle, pi plus 2 pi n. All this is over 3. So this is more like the generalized version, and not just restricting ourselves to one angle. Same thing here. So I have pi plus 360, which is 2 pi multiplied by n, and all this is over 3, like this. Now I can simply state to say where our n value will be 0, 1, or 2. Remember what I said, we need to find 3 values of z. So here's how we're going to do that. So let's pick this up, let's bring it up here. So our first task is to find, let's find z1, we'll call it z1. Now this is for n is equals to 0. So replace n with 0. Let's see what we get. So we can say z1 will be equals to 2 open bracket. So I have cos. Remember, if n here is 0, then the only thing that will remain with there will be pi over 3, because n is 0. So 2 pi cancels because n is 0. Then plus I sine, again there will just remain with pi over 3, like that. So our first value of z will be 2. Now cos pi over 3, remember pi over 3 is 60 degrees. So cos 60 degrees is simply half, and sine 60 degrees is the number root 3 over 2. Now there's an I here. So if 2 multiplies what we have here, then z1 is equals to 2 times half is 1, then 2 times root 3 over 2 is simply root 3. So root 3 I, So this is the first solution. Let's just write it here. So first solution will be 1 plus root 3 I. Okay, so let's move on. Second solution, we're going to set n. So I can say for z2, we can say for n is equals to 1. So this is the second solution for z. So z2, this time around, if I replace n with 1, remember I'm testing this one. We've done the 0 already. Now we're doing the 1, then we'll do the 2. So if I replace n with 1, this will become cos pi plus 2 pi. So pi plus 2 pi gives us 3 pi over 3 plus I sine. Same thing here. If I replace n with 1, it will be 2 pi. So pi plus 2 pi giving us 3 pi over 3. Now 3 pi over 3, the 3 cancels, leaving us with only pi. So this is 2, open bracket, cos pi plus I sine pi. Pi is 180 in degrees, so cos 180 is -1, and sine 180 is 0. So for this particular solution, we only have 2 multiplied by -1, giving us -2. So that's our second solution. Z2 is equals to -2. So we'll repeat the same process. That is now for Z3 when n is 2. So Z3 for n is equals to 2. So Z3 is equals to 2, open bracket. If I replace n with 2, I will say 4 pi plus pi, which is 5 pi. So that will be cos 5 pi over 3 plus I sine 5 pi over 3. Now in degrees, this is just 300. So if it's 300, then we have 2. Cos 300 is root 3 over 2, positive. And sine 300 is -half. So we have half I. So Z3 is equals to root 3 minus I. And that's our third solution. Root 3 minus I. So there you have it. These are the 3 solutions for our complex number Z.